What does it truly mean to times be times somewhere? Is it the unique collection of atoms that form your body standing on a specific patch of Earth, breathing a particular parcel of air? Or is it something more, a pattern, a consciousness, an intricate dance of information that defines you, independent of the physical matter you currently occupy? This question, once the exclusive domain of philosophers debating in candlelit rooms, has been catapulted into the heart of modern physics by a dream as old as storytelling itself. It's a fantasy woven so deeply into our cultural DNA that we can summon its image in a heartbeat, a shimmering column of light, a gentle hum that crescendos into a cascade of dissolving particles, followed by an impossible reappearance, light years away in the blink of an eye. The transporter, instantaneous travel, the ultimate liberation from the tyranny of distance. For more than half a century, this single breathtaking idea has served as the imaginative engine for our visions of the future. We've watched starship captains dematerialize on alien worlds, their forms dissolving into a stream of pure energy, only to be perfectly reassembled on a distant planet's surface moments later. We have accepted this miracle as a fundamental technology of tomorrow, a convenience as casual as a 21st century video call, yet more profound than anything humanity has ever achieved. It represents a mastery over the universe that feels almost divine, the power to deconstruct and reconstruct reality itself at will. This promise whispers of a future where borders are meaningless, where the vast, lonely emptiness of space becomes a traversable neighborhood. Imagine stepping onto a platform in London and before your next breath, feeling the warm sun of a Martian colony on your skin. Imagine a surgeon in Boston performing a life-saving operation on a patient in a deep space outpost in real time, her hands rematerializing in the operating theater a billion miles from her body. The implications are staggering, rewriting the very rules of exploration, commerce, medicine, and human connection. It's a dream of ultimate freedom, of being unbound by the slow, cumbersome vessel of the human body and the relentless, unforgiving clock of physics. But dreams, especially those so grand, must eventually face the harsh light of reality. And for the longest time, the scientific verdict on human teleportation has been unequivocal, a resounding and absolute no. The obstacles aren't merely technological. They appear to be woven into the fundamental laws of nature, forming a fortress of impossibility that seems utterly impenetrable. To understand the scale of this challenge, you must first think of yourself not as a person but as a collection of information. Staggeringly complex information. A single human body is composed of roughly 7 octillion atoms. That's a 7 followed by 27 zeros. To build an exact replica of you somewhere else, you would need to know the precise type, location, quantum, state, and velocity of every single one of those atoms. The amount of data required to store this cosmic blueprint is beyond astronomical. It would dwarf every word ever spoken, every book ever written, every byte of information currently stored on every computer on Earth, multiplied by factors that would exhaust our vocabulary for large numbers. Simply scanning and storing that data would require a computer with more memory than has ever been conceived. Even if you could somehow solve the data problem, you would immediately collide with a more profound barrier, a ghost in the atomic machine known as the Heisenberg uncertainty principle. This is one of the pillars of quantum mechanics, and it delivers a devastating blow to the classic sci-fi teleporter. It states that you cannot simultaneously know with perfect accuracy both the exact position and the exact momentum of a particle. The very act of measuring one property with high precision inherently scrambles the other. It's a law of cosmic fuzziness. Think of it like trying to read the fine print on a photograph of a speeding bullet. A fast shutter speed will give you a crystal clear image of the bullet's location, but you'll have no idea how fast it was going. A slow shutter speed will show you a blurry streak revealing its momentum, but its precise location will be a mystery. To perfectly teleport you, a machine would need to know both times for every single one of your 7 octillion atoms. The moment it tried to pinpoint an electron's location, it would obliterate the information about its momentum. The act of reading the blueprint would by definition destroy it. You would be trying to grasp smoke. And the challenges continue to cascade, each one more daunting than the last. Let us imagine for a moment that you overcome these hurdles. You have the data, you've somehow circumvented Heisenberg, and you've transmitted this impossibly large file across space. Now comes the reconstruction. Your destination teleporter must now become the most sophisticated 3D printer ever conceived, a quantum construction machine of unimaginable precision. It would need to grab individual atoms from a source material and place them in their exact positions with the correct energy states, connected by the correct chemical bonds, all in a matter of seconds. An error of a single nanometer, the misplacement of just one key molecule in the intricate architecture of a single neuron in your brain, could be the difference between you and a catastrophic biological failure. It's a task akin to reassembling a sandcastle grain by grain from a hurricane in the dark and getting every single grain back into its original place. The sheer energy required to power such a process would likely rival the output of a star. In the face of these colossal, seemingly absolute barriers, the dream of teleportation seems destined to remain exactly that, a beautiful but ultimately childish fantasy. And yet, science is a story of impossible barriers being overcome by radical new ideas. It's a tale of paradigms shifting, of realities being revealed to be far stranger and more flexible than we ever imagined. While the brute force method of scanning and reassembling matter is a dead end, a different path has quietly emerged from the deepest, most bewildering corner of physics. This path doesn't involve moving matter at all. It involves something far more ethereal, something that Einstein himself famously dismissed as spooky action at a distance. It requires us to abandon our common sense intuitions about how the universe works, and to embrace a reality governed by probability paradox and profound unseen connections. We must journey down to the subatomic realm, a ghostly world where particles can exist in multiple places at once, where the act of observation changes the outcome of an experiment, and where two particles once linked can remain mysteriously connected across any distance, their fates intertwined by an invisible, unbreakable thread. This phenomenon, known as quantum entanglement, is not a theory. It is a proven, tested, and foundational aspect of our universe. Entanglement is the key. It provides a loophole, a clever workaround to the seemingly insurmountable obstacles of classical teleportation. It suggests that you don't need to physically ship the atoms that make you times you asterisk. You only need to transmit the information, the unique quantum state that defines them. This is the revolutionary concept of quantum teleportation. It is not the transportation of matter, but the transportation of information. It works by creating a pair of entangled particles, let's call them A and B, and sending one of them, B, to a distant location. Back at the source, you take a third particle, C, the one whose state you wish to teleport, and you perform a special kind of measurement on it and particle A. This measurement does two things. It extracts some information about particle C, and because of the uncertainty principle, it simultaneously destroys its original state. But here is the miracle. Because A and B are entangled, the information extracted from C and A is instantly, and I mean instantly transmitted to the distant particle B. It doesn't travel through space in the conventional sense. The connection is non-local, a fundamental property of the universe's fabric. Particle B, light years away, is immediately transformed into a perfect replica of what particle C times used times to be. The original has been destroyed, but its exact quantum identity now exists somewhere else. This is not science fiction. In laboratories around the world, this very process has been successfully and repeatedly performed. Scientists have teleported the quantum state of single photons over hundreds of kilometers through fiber optic cables and even up to orbiting satellites. They have entangled larger and larger systems, moving from single particles to small collections of atoms. Each experiment is a small but monumental step, proving that the principle is sound. We have found a way to use nature's own spooky magic to move the essence of a thing from one place to another without it ever crossing the space in between. We are in a very real sense learning to write letters on one side of the universe that are instantly read on the other. The immense technological chasm between teleporting the state of a single atom and teleporting a human being remains, of course, almost comically vast. The 7 octillion atoms of your body represent a system of such staggering complexity that applying these principles to it remains far beyond our current horizon. But for the first time in history, the fortress of impossibility has been breached. The answer to whether teleportation is possible is no longer a simple no. It is now a far more tantalizing and far more complicated maybe. This new possibility, however, forces us to confront an even deeper, more unsettling question, one that brings us full circle to where we began. If we were to one day build a machine that could perform this incredible feat, a machine that scans every atom in your body, destroying the original in the process, while using quantum entanglement to perfectly reconstruct you on Mars, person who arrives on Mars truly times you times. A perfect copy has been created possessing all your memories, your thoughts, your feelings, your scars, your hopes, your fears. This new being would be convinced it was you remembering stepping into the machine on Earth just moments before. To all outside observers, it would be indistinguishable from you. But did times you times travel, or did you simply die on Earth replaced by a flawless clone who has inherited your life? This is the ship of Theseus, Paradox reborn for the quantum age. If you replace every plank of a ship one by one, is it still the same ship at the end? If you are deconstructed atom by atom, is the reassembled pattern still you? This question strikes at the very heart of what we believe, consciousness and identity to be. Are we merely the sum of our physical parts, a temporary arrangement of matter, or is there a continuity of experience, a stream of consciousness that cannot be copied or transferred? Is your soul, for want of a better word, in the data or in the material? The science of quantum teleportation, for all its promise, offers no easy answers here. It presents us with a future where we may have to choose between our desire for ultimate freedom and our very definition of self. The journey to understand this technology is therefore more than a scientific quest. It is a philosophical odyssey. It will force us to explore the strangest corners of the quantum world, to meet the brilliant minds pushing the boundaries of what's possible, and to confront the profound implications of their work. We will have to grapple with the nature of information, the fabric of reality, and the very essence of what it means to be human. To begin that journey to truly comprehend how this cosmic magic trick is even remotely feasible, we must first venture deep into the bizarre and unbreakable bond that started it all, the eerie, intimate connection known as quantum entanglement. What if you aren't really here, not in the way you think? What if the essential truth of your existence, the very blueprint that makes you times, is not the physical collection of atoms reading these words, but a delicate, impossibly complex pattern of information, a quantum recipe so precise that if copied and transmitted could rebuild you atom for atom somewhere else entirely? This idea, the dream of teleportation, seems like the ultimate futuristic fantasy. But its roots lie not in the distant future, but deep in the past, born from a moment when our entire conception of reality was shattered. To understand how we might one day travel at the speed of light, we must first journey back to a time when the universe as we knew it began to unravel. We begin at the dawn of the 20th century, an age of supreme confidence. Humanity had seemingly conquered the material world. The laws of physics laid down by giants like Newton appeared complete, a perfect and predictable clockwork mechanism governing everything from the fall of an apple to the majestic dance of the planets. The universe was a grand, deterministic machine, and we were its masters. There were just a couple of small nagging problems, tiny clouds, on an otherwise brilliant blue sky that most physicists assumed would soon be tidied up, folded neatly back into the existing theories. But these were not clouds. They were the harbingers of a storm that would tear down the entire edifice of classical thought, a revolution that would begin not with a bang but with a faint, inexplicable glow. The puzzle was a strange one, lurking in the heat of a furnace, in the heart of a flame in the light from a simple, glowing hot object. The problem was colour, or more precisely the spectrum of light emitted by what physicists call a black body, a perfect absorber and emitter of radiation. Classical physics made a confident prediction about this glow. As an object got hotter, it should radiate energy across all wavelengths, with the intensity increasing dramatically for shorter, more energetic wavelengths like ultraviolet light. The equations were clear, unambiguous, and utterly catastrophically wrong. They predicted that any hot object should be unleashing an infinite amount of energy in the ultraviolet spectrum, a blinding, lethal torrent of radiation that would instantly sterilize the universe. This spectacular failure was so profound it earned a terrifying name, the ultraviolet catastrophe. It was as if the universe had a fundamental mathematical error, a scream into infinity that our best science simply could not silence. Into this crisis stepped a reluctant revolutionary, a German physicist named Max Planck. Planck was a man steeped in the classical tradition, a conservative thinker who deeply respected the old ways and had no desire to tear them down. He wrestled with the black body problem for years, trying every conventional trick he knew to make the equations work, to reconcile observation with the elegant theories of his predecessors. Nothing worked. Finally, in a moment he would later describe as an act of desperation, he decided to try something that went against every instinct he possessed. He cheated. He proposed that energy was not a smooth, continuous wave as everyone had believed for centuries. Instead, he imagined it was choppy, grainy, coming only in tiny, discrete packets like currency that exists only as coins, not as a continuous flow of value. He called these indivisible energy packets quanta. It was a purely mathematical trick, a fudge factor designed to stop the equations from screaming into infinity. By making energy discrete, he could perfectly predict the observed glow of a hot object. The math worked. It worked beautifully. But the physical implication was monstrous. It meant that at the very smallest scales, reality wasn't smooth at all. It was pixelated. It meant a pendulum couldn't just have any times energy, but only specific allowed amounts. It was like saying you could walk up a ramp, but only by taking steps of a specific non-negotiable height. Planck himself was horrified by his own idea, hoping it would eventually be explained away as a mere accounting tool. But the genie was out of the bottle. He had unknowingly pried open a doorway into a new reality, and a young patent clerk in Bern, Switzerland, was about to kick that door wide open. That clerk was Albert Einstein. In 1905, his miracle year, Einstein took Planck's desperate idea and declared it to be a physical reality. He used the concept of quanta to solve another nagging puzzle, the photoelectric effect, where light hitting a metal surface could knock electrons loose. He argued that light itself was made of these quanta particles we now call photons. Light, which had been definitively proven to be a wave, was suddenly acting like a stream of tiny bullets. This dual nature, this impossible contradiction of being both a wave and a particle at the same time, was the first true glimpse of the sheer weirdness that was to come. The quantum revolution had its first confirmed physical evidence. The old world of absolute certainty was beginning to die, and the new world of probability and paradox was being born. The mystery then deepened, moving from the nature of light to the very heart of matter, the atom. For decades, the atom was imagined as a plum pudding, a blob of positive charge with tiny negative electrons scattered throughout. But in 1909, an experiment by Ernest Rutherford fired tiny particles at a thin sheet of gold foil and found that while most passed through, some bounced back as if they had hit a solid wall. The atom, he realized, was mostly empty space. It had a tiny, incredibly dense, positively charged nucleus at its center, with the electrons orbiting it like miniature planets around a sun. This planetary model was elegant, intuitive, and according to the laws of classical physics, completely impossible. The problem was simple and deadly. An orbiting electron is an accelerating charge, and classical electromagnetism demanded that any accelerating charge must radiate energy away. An electron in Rutherford's atom should therefore be constantly losing energy, spiraling inwards in a fraction of a second and crashing into the nucleus in a puff of radiation. Every atom in the universe should have collapsed the instant it was formed. The fact that you are here, that the world exists, that matter is stable, was a profound and terrifying violation of the known laws of physics. The universe itself had become the greatest unsolved mystery. It was a Danish physicist, the brilliant and visionary Niels Bohr, who provided the next piece of the puzzle. Visiting Rutherford's lab, Bohr was struck by the atom's impossible stability. He took Planck's radical idea of quanta and applied it directly to the structure of matter. He proposed that electrons could not orbit the nucleus just anywhere they pleased. They were restricted, locked into specific allowed orbits, like trains on a predetermined set of tracks. They could exist in one orbit or another, but never in between. To move from a higher orbit to a lower one, an electron would emit a single precise quantum of light, a photon. To jump up, it had to absorb one. And while in one of these stationary states, it simply did not radiate energy. It broke the classical rules because at the atomic scale, those rules no longer applied. This was a shocking proposition. Bohr's model explained why atoms were stable and why elements emitted light only at specific signature frequencies. But it introduced an even more baffling concept, the quantum leap. When an electron jumped between orbits, it did so instantaneously. It did not travel through the space in between. It simply ceased to exist in one place and simultaneously began to exist in another. This wasn't just a new rule. It was a fundamental assault on our understanding of space, time, and motion. And it was just the beginning. The world Bohr and his contemporaries were uncovering was one governed not by certainty but by strange, rigid laws and sudden, inexplicable jumps. The 1,920 seconds became the heroic age of quantum physics. At legendary conferences like the Solvay Conference in Brussels, the greatest minds on the planet gathered to argue, to collaborate, and to grapple with the terrifying implications of their own discoveries. A new generation of physicists, Werner Heisenberg, Erwin Schrödinger, Wolfgang Pauli, Paul Dirac, began to build the full mathematical framework of this new science, a theory they would call quantum mechanics, and with every new equation, reality seemed to get stranger. They discovered that the contradictions were not just apparent, they were fundamental. The wave-particle duality that Einstein had revealed for light was true for matter as well. An electron, a proton, even a whole atom was both a particle and a wave simultaneously. This led to one of the most profound and unsettling ideas in the history of science: superposition. Werner Heisenberg's famous uncertainty principle showed that there was a fundamental limit to what we could know about a particle. The more precisely you measured its position, the less precisely you could know its momentum, and vice versa. It wasn't a failure of our instruments, it was a built-in feature of the universe. The very act of observing a quantum system irrevocably changed it. Erwin Schrödinger captured this idea in a powerful mathematical tool known as the wave function, which described a particle not as a tiny point, but as a ghostly cloud of probabilities, a smear of potential existence. Before you look, a particle isn't in any single place. It is in a state of superposition, existing in all its possible states at once. An electron isn't here times or times there. It is simultaneously here times and times there, and everywhere else it could possibly be described only by a wave of probability. Think of a spinning coin. While it's in the air, it is neither heads nor tails. In a way, it is both at the same time. Only when it lands, when it is measured or observed, does it collapse into one definite state. The quantum world, it turned out, was a realm of pure potential, a symphony of possibilities that only snapped into a single concrete reality when the universe or an observer within it forced its hand. This idea was so bizarre, so contrary to all human intuition, that physicists spent years arguing over what it truly meant. Was the particle really in multiple places at once? Or was the math just a convenient way of describing our own ignorance? For Niels Bohr and his Copenhagen interpretation, the answer was clear, and uncompromising. The quantum world simply did not have definite properties until they were measured. The unobserved reality is a phantom, a fog of potential. But out of the very same mathematics that described this ghostly superposition, another, even more mystifying prediction emerged. It was a consequence so bizarre, so seemingly impossible, that it would shake Albert Einstein to his core and lead him to dismiss it with a now famous phrase, spooky action at a distance. This phenomenon is the second and perhaps most crucial key to unlocking the dream of teleportation. It is called quantum entanglement. The theory predicted that you could have two particles, say two electrons, which are created or interact in such a way that their quantum states become inexorably linked. From that moment on, they are no longer two separate entities, but in a profound sense a single system described by a single wave function, no matter how far apart they travel. Imagine two particles, A and B, entangled in their property of spin, which can be measured as either up or down. According to the principle of superposition, before you measure them, neither particle has a definite spin. Each is in a ghostly state of being both up and down at the same time. But because they are entangled, their fates are intertwined. The math dictates that if you measure particle A and find its spin is up, you will know instantly and with absolute certainty that the spin of particle B is down and vice versa. This in itself might not seem so strange. Imagine you have a pair of gloves. You put one in a box and the other in a second box. You ship one box to the other side of the galaxy. When you open your box and find a left-handed glove, you instantly know the other box contains a right-handed glove. There's nothing mysterious about that. The information was predetermined from the start, but entanglement is not like that. In the quantum world, the particles do not have a definite spin before you measure them. They are not gloves that were secretly left or right-handed all along. They are in a state of pure, undefined potential. It is only the act of measuring the first particle that seems to instantaneously force the second particle, no matter how distant, to choose the opposite state. This connection, this correlation, appears to happen faster than the speed of light. If you measure particle A on Earth, its partner particle B in the Andromeda galaxy would instantly snap into the opposite state. Information, the result of the measurement, seems to be violating Einstein's own cosmic speed limit, the foundational principle of his theory of relativity. For Einstein, this was a clear sign that quantum mechanics was incomplete. There had to be hidden variables, some secret information like the glove's handedness that the particles carried with them all along. The connection couldn't possibly be real. It was too spooky a ghostly link that defied the logical structure of space and time. He was convinced that the universe at its heart could not be this strange. For decades, this debate remained a philosophical one, a clash of titans between Bohr's acceptance of the bizarre and Einstein's insistence on a deeper, more sensible reality. They were wrestling with the soul of the universe. What they did not know, what they could not have possibly imagined, was that in their abstract arguments about ghostly connections and collapsing probabilities, they had uncovered the two fundamental tools required for the most audacious technological leap imaginable. Superposition provided a way to encode information into the fragile, undefined state of a quantum particle. And entanglement, Einstein's spooky action, offered a seemingly impossible conduit, a cosmic communication channel woven into the very fabric of reality itself. These pioneers were not trying to invent a teleporter, they were simply trying to read the book of nature, to comprehend a language more alien and more profound than they had ever anticipated. They had laid the conceptual groundwork, discovering a world where information was not just written down, but existed as a state of pure potential, a world where distant points in space could be bound by an unbreakable, instantaneous thread. The great philosophical puzzles of the 1,920 seconds had become the engineering challenges of the future. The question was no longer just about understanding this bizarre quantum realm. The next audacious question would be, could we learn to control it? Could we harness this spooky connection not just to send a message, but to send the very pattern of existence itself across the void? And so for decades, the dream of teleportation remained chained by the laws of physics. A tantalizing fantasy confined to the pages of fiction. The universe, it seemed, had drawn a firm line. You could travel, you could communicate, but you could not simply times be times here and then in a blink times be times there. The very notion felt like a violation, a form of cosmic cheating. Yet in the quiet hum of academic thought, a revolution was brewing, a subtle tremor that would soon shake the foundations of what we thought was possible. The year was 1993. 6 brilliant minds scattered across the globe were about to publish a paper. It was not a grand announcement made from a podium, but a dense mathematical document that to the uninitiated would look like gibberish. To a physicist, however, it was a piece of dynamite. Charles Bennett, Gilles Brassard, Claude Crépeau, Richard Josser, Asher Perez, and William Wouters had not broken the laws of physics. They had found a hidden doorway. They had discovered a way to leverage the universe's most profound and perplexing mystery, quantum entanglement, to achieve the impossible. Their proposal was elegant, audacious, and profoundly strange. It did not involve deconstructing a physical object atom by atom. That was the brute force method, the stuff of engineering nightmares. This was something different, something more fundamental. They argued that you didn't need to send the times matter asterisk. You only needed to send the times information asterisk. Not just any information like the words on a page, but the deepest, most complete description of an object that reality allows its quantum state. Think of it as an object's soul, its true, unrepeatable identity containing all the probabilities of its existence. This state is impossibly fragile. The very act of looking at it, of measuring it, destroys it forever. How could you possibly read this quantum soul in one place to rebuild it in another? This was the central paradox. Their paper was the answer. They had devised a method, a celestial sleight of hand that could transmit a perfect quantum state from one location to another without that state ever traveling through the intervening space. They called it Quantum Teleportation. The dream, it turned out, was not dead. It was just waiting for the right key. To understand this breakthrough, you must discard your notions of everyday transportation. We are not mailing a package. We are orchestrating a resurrection. Imagine three key players in this cosmic drama. First, there is Alice, our sender. She possesses a single precious particle, let's call it particle X, whose quantum state she wants to teleport. This state is a secret, a delicate whisper of information that defines particle X completely. The profound catch is that even Alice cannot know this state. According to the laws of quantum mechanics, the moment she tries to measure it to learn its secret, she will irrevocably alter it, destroying the very information she wishes to send. Particle X is like a dream you can only remember by never waking up, so Alice holds this quantum enigma, a message in a bottle that she can never open. Our second player is Bob, the receiver located light years away. His task is to create a perfect, identical replica of Alice's particle X. How can he do this if Alice can't even tell him what particle X is like? This is where the third and most crucial player enters the scene, a pair of entangled particles. These are not just any two particles. They are what Einstein, in his profound skepticism, famously called spooky. Forged together in a single quantum event, they are now separated, one given to Alice, the other to Bob. No matter how vast the gulf of space between them, a millimeter or a million light years, they remain intrinsically linked. They are two bodies with a single soul. They behave as a single entity, a unified quantum system. If Alice measures a property of her entangled particle, say its spin, Bob's particle at that exact same instant will adopt a perfectly correlated spin. There is no signal that travels between them. This isn't communication, it's a shared reality. This ghostly connection, this non-local bond that defies our classical intuition, is the secret channel. It is the quantum bridge upon which this impossible journey will be made. Alice now possesses two particles, the original she wants to send particle X, and her half of the entangled pair. Bob, far away, patiently waits, holding his half of that same entangled pair. The stage is set. The procedure begins with an act of profound sacrifice. Alice must perform a special kind of measurement, a joint measurement on both the particles in her possession, the original particle X, and her entangled particle. This is no simple observation. It is a sophisticated quantum interrogation known as a Bell state measurement. In this single decisive act, she forces these two particles to interact to reveal how they are related to each other. The result of this measurement does not tell her the original secret state of particle X. That information remains forever hidden from her. Instead, she gets one of four possible outcomes, a simple classical result. Think of it as a number 1, 2, 3, or 4. But in that moment, something extraordinary and irreversible happens. The very act of Alice's measurement destroys the original state of particle X. It is gone, vanished from her location completely. Simultaneously, that same measurement also breaks the entanglement that connected her particle to Bob's. The spooky, instantaneous connection across the cosmos is severed. It seems like a catastrophic failure. The original has been annihilated, and the bridge to Bob has been burned. But this is where the genius of the 1993 blueprint reveals itself. The destruction was not an accident. It was a necessary part of the transfer. The information that once defined particle X has not truly vanished. Instead, it has been imprinted onto the relationship between all three particles, its ghost now haunting the entire system. Alice's classical result that 1, 2, 3, or 4 is the key. It is the final piece of the puzzle, the instruction manual that Bob desperately needs. This information is not quantum. It is ordinary classical data, just a few bits. Alice must now send this information to Bob through a conventional channel. She can pick up a phone, send a text message, or transmit a radio signal at the speed of light. This is a crucial point. Because this classical message is limited by the universal speed limit, quantum teleportation cannot be used for faster-than-light communication. The spooky part of entanglement doesn't transmit useful information on its own. It only establishes a correlation. The teleportation is only completed once the classical message arrives. Far away, Bob receives this mundane message from Alice. Let's say she sent him the number 3. To Bob, this number is a precise set of instructions. It tells him exactly what to do to times his entangled particle, the one he has been holding all this time. The message might as well say, rotate your particle 90 degrees around the z-axis and flip it on the x-axis. He applies a specific, simple transformation, a flick of a quantum wrist to his particle, and then the miracle occurs. The moment he completes the operation, his particle is transformed. It is no longer just one half of a broken, entangled pair. It has become a perfect, flawless replica of Alice's original particle X. It possesses the exact same quantum state, the same secret identity, the same informational soul that existed moments ago, light years away. It is not a mere copy. In the quantum world, where identity is defined by state, it times is times the particle. The original was destroyed, and from its ashes a new one has been reborn, reconstituted across the void. The state itself, the very essence of the particle, has leaped across space, its journey instantaneous, its arrival heralded only by a burst of classical information traveling at the finite speed of light. For 4 years, this breathtaking idea remained a masterpiece of theoretical physics, a perfect equation on a blackboard. It was a promise of what the universe could do, but a promise unfulfilled. The chasm between theory and practice can be immense, and building a machine to perform this delicate quantum surgery was a challenge of staggering proportions. The world's leading experimental physicists entered a quiet, intense race. The challenge was to isolate and control single quantum systems with a precision previously unimaginable, shielding them from the slightest tremor or stray photon that could shatter their fragile states. The first to cross the finish line was a team led by the Austrian physicist Anton Zeilinger. In 1,997 inches, a darkened laboratory in Innsbruck, they achieved the impossible. They teleported the quantum state of a single photon. Their setup was a labyrinth of lasers, specialized crystals, mirrors and beam splitters, an optical maze designed to coax particles of light into performing this intricate ballet. They would generate a pair of entangled photons, sending one down a fiber optic cable to a receiver. The other was directed to a station where it met a third photon, the one whose state was to be teleported. Imagine the tension in that lab. They had to ensure that the 2 photons at Alice's station arrived at the Bell state detector at the exact same femtosecond, a meeting so precisely timed, it's like 2 arrows hitting each other in midair. The detectors themselves were marvels capable of registering the arrival of a single particle of light. For hours, they would run the experiment, watching for the telltale clicks of the detectors that would signal a successful teleportation event. The clicks were rare, the successes buried in a mountain of failures and noise, but when the data was analyzed, the conclusion was inescapable. They would prepare the initial photon in a specific polarization state, say horizontal. They would run the teleportation protocol, and on the other side of the lab, after the classical information was received and the correction applied, they would measure the resulting photon. Time and time again, it emerged with that same horizontal polarization. They tried other states, vertical, diagonal, and each time the teleported photon perfectly matched the original that had been destroyed. It was a resounding triumph. The abstract theory of 1,993 was now a concrete reality. Humanity had taken its first tiny step into a world of quantum transport. This initial success with photons was like the Wright brothers' first flight at Kitty Hawk. It was a short hop, but it proved that flight was possible. Photons, being particles of light, are ideal candidates for these first attempts. They are swift, relatively easy to produce and entangle, and most importantly, they are standoffish. They don't interact strongly with their environment, which helps preserve their delicate quantum states, a property known as coherence. But to truly advance the technology, scientists knew they had to move beyond light. They had to teleport the state of particles that have mass particles that form the very substance of our world. The next great leap came just a few years later with the teleportation of the state of an atom. This was a monumental increase in complexity. Unlike a fleeting photon, an atom is a far more substantial and intricate entity. It has mass and internal structure of protons, neutrons, and electrons. It feels the pull of gravity and is easily disturbed by stray electromagnetic fields. Taming an atom for teleportation requires putting it in a state of extreme solitary confinement. Scientists at the National Institute of Standards and Technology achieved this using an ion trap, a microscopic prison crafted from electric and magnetic fields. Within this invisible cage, they could hold a single charged atom or ion, levitating it in a near-perfect vacuum, shielded from the noisy outside world. Here, lasers could be used with surgical precision to cool the atom to a near standstill, just fractions of a degree above absolute zero, and to manipulate its internal quantum energy states. The experiment was an entirely new level of technical mastery. They entangled 2 beryllium ions, then introduced a third whose state they wanted to teleport. The process was the same in principle, a Bell state measurement, a classical signal, a final corrective operation, but the physical machinery was vastly more complex. When it worked, the implications were profound. They had teleported a property of matter itself. The informational soul of a physical object had been extracted, sent as a ghostly message, and imprinted onto a distant waiting twin. The dream was no longer confined to the ethereal realm of light. It had gained a foothold in the material world. From these seminal victories, the field exploded with progress, each new experiment pushing the boundaries further. Scientists learned to teleport information not just between identical particles, but between completely different ones, such as from a photon to an atom. This was a critical development, a quantum Rosetta Stone that could translate information between fast-moving flying qubits, perfect for communication, and stationary storage qubits, ideal for computation. The distances grew longer, from across a lab bench to across a river, then between 2 different cities. In 2017, a Chinese satellite named Misius teleported the state of a photon from a ground station in Tibet to orbit over 500 kilometers straight up into the vacuum of space. The quantum bridge now spanned from the Earth to the heavens. The fidelity of the process, the accuracy of the teleported state improved dramatically, reaching levels of near perfection. Scientists even managed to teleport more complex information, not just the state of a single particle, but the entangled state shared between 2 particles, effectively entangling the entanglement. Each of these experiments, each painstaking success built upon the last, served to solidify one astonishing fact. Quantum teleportation is not a fluke. It is a fundamental, repeatable, and increasingly controllable process woven into the fabric of reality. We have mastered the basic grammar of this new cosmic language. We have learned to whisper a quantum secret in one corner of the universe and have it heard perfectly in another. We have demonstrated beyond any doubt that the essence of an object can be separated from its substance, that its identity can be made to leap across the void. The theory of 1993, once a daring piece of speculation, is now the bedrock of a burgeoning technological revolution. We stand in a new world armed with a power that our ancestors could not have even imagined. The principle is proven. The technology at this microscopic scale is real. But this very success forces us to confront a far more daunting and spectacular question. We have teleported a single photon, a lone atom. What would it take to teleport something infinitely more complex? What would it take to teleport a living thing, a conscious mind, a human being? The gap between a single qubit and the seething, intricate cosmos of a human body isn't the abyss of complexity so vast it challenges our very ability to comprehend it. That ghostly handshake, that instantaneous connection we've witnessed between single particles of light, represents one of the most profound victories in modern physics. It feels like a key turning a lock in the very fabric of reality. But a single key opening a single lock is a far cry from building a doorway. After proving that the quantum state of one photon could be perfectly imprinted upon another, the next question became not one of principle, but of ambition. Could we teach this quantum ghost to carry more than a single secret? Could we move beyond one particle, beyond one simple property, and teleport something with even a whisper of complexity? This wasn't merely a desire for a more impressive magic trick. It was the first tentative step on an impossibly long road, a journey to see if this strange new physics could ever be scaled. The initial challenge was to teleport more than a single qubit of information. Imagine trying to describe a person using only one word. You might say tall or fast, but you would have captured almost nothing of their true essence. The first quantum teleportation experiments were like that, conveying only a single binary property, a spin-up or a spin-down, a horizontal or vertical polarization. To teleport anything meaningful, scientists had to learn how to entangle and transmit a chorus of properties simultaneously. This meant creating far more intricate states of entanglement, not just a pair of linked photons, but a whole family of them, a delicate web of quantum correlations. The slightest disturbance to any single particle in this web, any stray photon or thermal vibration from the lab equipment, could bring the entire structure crashing down in a process we call decoherence. It was like trying to conduct a silent orchestra in the middle of a hurricane. The symphony of quantum states had to be perfectly preserved, shielded from the noisy classical world that relentlessly sought to tear it apart. Then came the leap to matter itself. While photons are magnificent carriers of information, they are fleeting and massless. Could this trick be performed on particles that have substance particles that form the very bedrock of our existence? In laboratories shrouded from electromagnetic interference, cooled to fractions of a degree above absolute zero, researchers turned their attention to atoms. Using a breathtaking combination of lasers to trap and cool individual atoms of elements like calcium or beryllium, they held them in a state of near-perfect stillness, a gravitational and energetic stasis. Here they could manipulate the atom's quantum state, its spin, its energy level, and entangle it with a photon. The process was a masterpiece of control. A laser would excite the trapped atom, causing it to emit a single photon. By the unbreakable laws of quantum mechanics, that photon's properties were now inextricably linked with the atom it left behind. They were entangled. That photon, the emissary, would then be sent on a journey perhaps only a few meters across the lab to a second distant atom. There, a complex series of measurements would be performed on the traveling photon, and the second atom, a quantum interrogation that would, once the results were classically communicated back to the first station, allow scientists to perfectly reconstruct the original atom's quantum state in its distant twin. They had done it. They had teleported the complete quantum state of a single atom. It was a monumental achievement, a bridge between the ethereal world of light and the tangible world of matter. Yet the scale remained achingly small. A single atom, two properties, and the distance, a few meters. To the public, it might have seemed like a snail's pace, but for the scientists involved, each additional meter was a hard-won battle against the universe's innate tendency towards chaos. The quantum world you see does not like to be stretched. That delicate thread of entanglement is fragile, and the longer it gets, the more opportunities the environment has to sever it. The first long-distance attempts were fraught with failure. Imagine trying to throw a single grain of sand across a windy canyon and have it land on a specific target the size of a pinhead. That was the challenge. The canyon was the laboratory filled with thermal noise, stray magnetic fields, and the vibrations of the building itself. The wind was decoherence, the constant invasive whisper of the classical world that corrupts quantum information. The first major breakthrough in conquering distance came not from building better shields, but from choosing a better path: fiber optics. The same glass threads that carry our internet data, our phone calls, and our television shows became the new highways for quantum information. By encoding the quantum state onto a photon of a specific wavelength, one that traveled with minimal loss through optical fiber, researchers could begin to push the boundaries of their labs. The race was on. In 2004, a team in Vienna successfully teleported a photon state over 600 meters through a fiber optic cable running under the river Danube. It was a stunning proof of concept, demonstrating that quantum information could survive a journey outside the pristine, controlled confines of a laboratory. The success emboldened teams around the world. The distance began to climb. First a few kilometers, then 10, then 25. With each new record, new technical hurdles had to be overcome. Specialized detectors so sensitive they could reliably register the arrival of a single photon had to be invented. Methods for synchronizing atomic clocks at both ends of the fiber to within trillionths of a second were perfected, ensuring that the measurement at one end could be precisely correlated with the operation at the other. But fiber optics, for all their utility, have a fundamental limit. Over long distances, even the purest glass absorbs and scatters light. The signal, which already consists of single lonely photons, grows fainter and fainter until it is completely lost in the inherent noise of the system. Amplifying the signal, as we do with classical internet data, is impossible. The very act of observing a quantum particle to amplify it destroys the fragile state we are trying to teleport. This is a hard limit dictated by the no-cloning theorem, a fundamental pillar of quantum mechanics. It states you cannot create an identical independent copy of an arbitrary unknown quantum state. You can't just copy and paste a qubit. By the early 2010 seconds, researchers had managed to teleport quantum states over 100 kilometers of spooled fiber in a lab and nearly 150 kilometers in real-world networks. Yet this seemed to be the ceiling. To span continents or oceans, a new path was needed. If we couldn't go times through times the world, we would have to go times over times it. The next great leap would require leaving the planet entirely. The ultimate high ground was space. The vacuum of space is a far gentler medium for a photon than even the purest optical fiber. Once a photon escapes Earth's turbulent atmosphere, it can travel for thousands of kilometers with almost no chance of being disturbed. The challenge, however, was astronomical in its own right. It required building a satellite, a quantum laboratory in orbit capable of generating and detecting single photons. It required ground stations with telescopes that could aim a laser beam with pinpoint accuracy, tracking this satellite as it hurtled through the void at over 17,000 miles per hour. This is like trying to hit a moving dime from 20 miles away with a laser pointer. In 2016, the world watched as China launched the MISSIUS satellite, the world's first quantum science satellite, a half-ton testament to this audacious goal. From a remote observatory in the Tibetan mountains, scientists beamed a laser up to the heavens. This laser didn't carry data in the classical sense. Instead, it was a source of entangled photon pairs. One photon from each pair was kept at the ground station in Tibet, while its entangled twin was beamed up to the MISSIUS satellite as it passed overhead over 500 kilometers above. The satellite's sensitive detectors would catch this photon, measure its quantum state, and then the satellite would act as a trusted relay. Now imagine two ground stations separated by over 1,200 kilometers a distance, utterly impossible to bridge with fiber optics. As MISSIUS flew between them, it would generate its own pairs of entangled photons, beaming one twin down to the first station and the other twin down to the second. In a series of groundbreaking experiments, the teams used MISSIUS to achieve things previously confined to science fiction. They distributed entangled particles between two locations on Earth, separated by a record-shattering 1,200 kilometers. Then came the ultimate test. They generated an entangled pair on the ground, sent one of the photons up to the orbiting satellite, performed the Bell state measurement in orbit, and then beamed the classical information back down to Earth, where the other photon's state was successfully transformed. They had performed quantum teleportation from the Earth to orbit, spanning a distance of up to 1,400 kilometers. The MISSIUS experiments were a profound statement. They proved that the spooky action at a distance Einstein was so wary of was not confined to a laboratory bench. It wasn't an artifact of short-range physics. The ghostly connection of entanglement persists over vast astronomical distances, unhindered by space or time in the way we classically understand them. We had conquered distance. We had proven that the fundamental principle could be stretched across a continent. The doorway seemed to be swinging open. But it is here at this moment of triumph that we collide with the most sobering wall of all. It is the wall of complexity, the wall of scale, and it is this wall that separates the teleportation of a single particle's quantum information from the dream of teleporting a living, breathing human being. What we have accomplished so far is akin to learning how to perfectly transmit the sound of a single pure musical note across a vast ocean. What we need to do to teleport a person is to transmit an entire symphony with trillions upon trillions of instruments, each playing its own unique and impossibly complex part, without a single one of them missing a beat or playing a wrong note. Let us for a moment be brutally honest about the numbers. The single qubit of information we teleported from the ground to the Mickey's satellite represents one binary choice, a 0 or a 1. A single atom is a bit more complex, but its quantum state can still be described by a handful of numbers. Now consider the object you want to teleport you. Your body is composed of roughly 7 octillion atoms. That's a 7 followed by 27 zeros. 7,000 million atoms. To teleport you, we would first need to know the exact quantum state of every single one of those atoms simultaneously. We would need to know the position, the momentum, the spin, and the energy level of every electron, every proton, and every neutron. We would also need to know the state of every interaction and every entanglement between all of those particles. The amount of information this represents is not just large, it is hyper-astronomical, a number that defies all human comprehension. Let's try to put it in perspective. The number of classical bits required to store the complete quantum blueprint of a single human being would be a 10 raised to the power of 10 to the 28th power. How big is that number? If you were to write it out with one digit written on every single proton, neutron, and electron in the known universe, you would run out of universe before you could even begin to write the number down. It is a quantity of data so colossally vast that it makes the entire digital footprint of humanity, every email, every movie, every website, every scientific paper ever created, seem less than a single grain of sand on all the beaches of the world. This is the information problem, and it is a mountain so high it scrapes the ceiling of possibility itself. But let's assume through some physics, we can't yet imagine that we could somehow scan and record this information. Now we have to transmit it. The Mickey's satellite transmitted classical information via radio waves to complete the teleportation. To transmit your quantum blueprint, even using the most advanced communication channels conceivable would take longer than the current age of the universe. By the time the information arrived to reconstruct you, the star you left behind would be a cold, dead cinder. And even beyond the information and time problems lies the most delicate challenge of all fidelity and measurement. The Heisenberg uncertainty principle tells us that we cannot simultaneously know with perfect accuracy certain pairs of properties, like a particle's position and its momentum. The very act of measuring one property with precision introduces uncertainty into the other. How then could we possibly perform a complete Bell state measurement on an entire human body? The process of scanning you with such unimaginable precision would likely require energies so immense they would instantly vaporize you. It would be like trying to read a book by setting it on fire and analyzing the smoke. You would destroy the original in the most absolute sense imaginable just to get a partial flawed reading. Any error, any single misplaced atom or incorrectly assigned quantum state in the reconstruction process would be catastrophic. A tiny data corruption in your brain's neural map might not just erase a memory, it could fundamentally alter your personality, your consciousness, your very sense of self. What does a rounding error look like when applied to a soul? This is the turning point. This is the moment where the exhilarating ascent of scientific discovery meets the sheer vertical cliff face of cosmic scale. In conquering the kilometer, we have revealed the light years that still separate us from the dream. We have proven that the physics of teleportation is not a lie, that the universe does indeed permit this strange and wonderful quantum connection. But in doing so, we have also uncovered a truth that is both humbling and profound. The universe may allow it for a photon, but it has built creation from a single cell to a thinking human being with a level of complexity so far beyond our technological grasp that it borders on the divine. The challenge of scaling up is not just a matter of building a bigger machine, it's a fundamental confrontation with the sheer information density of matter itself. The question is no longer simply, how do we do it? The question has become, is the universe even willing to let us try? To have witnessed the delicate quantum waltz of a single atom teleported flawlessly across a laboratory is to feel the future crackling in the air. The principle, once a phantom of science fiction, has been proven. We have sent a whisper of reality across the void, a single note of the universe's song, and had it arrive perfectly in tune at its destination. From this triumphant peak of scientific achievement, it is so tempting, so human to look towards the ultimate horizon ourselves. If we can teleport one particle, then why not the trillions upon trillions that assemble into a thinking, feeling, living being? The journey from a single atom to a human being, however, is not a simple matter of scaling up. It is not a ladder we can climb. It is a leap across a chasm so wide, so profoundly deep, that to even gaze into its depths is to confront the very limits of what may be possible. The breathtaking success we have just celebrated now serves as the starkest launching point for our descent into an abyss of complexity, a confrontation with obstacles so gargantuan they resemble not engineering problems, but fundamental stochasm, laws of nature standing as cosmic sentinels barring our bee's path. The dream of human teleportation, born in the sterile quiet of the laboratory, is about to collide with the chaotic, thunderous reality of you. Imagine for a moment the blueprint of you, not the genetic code, that elegant but relatively simple spiral of information. We are speaking of something infinitely more detailed. We mean the quantum blueprint, the exact instantaneous state of every single particle that constitutes your body. Let us begin with the atoms, the building blocks. An average human body is composed of roughly 7 octillion atoms. That is a 7 followed by 27 zeros. It is a number so vast that it mocks comprehension. If each atom in your body were a single grain of sand, you could create more than 100 Earth-sized planets, each one a desert world covered entirely in sand. But this is still a gross oversimplification. The true challenge is not the number of particles, but the sheer volume of information they encode. Each of these 7 octillion atoms is itself a complex system of electrons, protons, and neutrons. Each of these subatomic particles possesses a suite of quantum properties: its position, its momentum, its spin, its energy state, its entanglement with its neighbors. To teleport you, we would need to know the precise value of every one of these properties for every single particle at the exact same moment in time. This isn't a list of ingredients. It is a perfect frozen snapshot of a dynamic living symphony. The information required to describe this single quantum state of your body would be staggering. How much data are we talking about? Scientists have attempted to estimate it. The numbers they arrive at are so large they require new language to articulate. It would not be measured in gigabytes or terabytes, or even the yottabytes that currently define the entire digital content of our planet. The complete quantum description of a single human being would likely amount to something in the order of 10 to the power of 10 to the 28 bits. It is a number that, if you were to write it out, would not fit within the observable universe. All the data ever generated by humanity, every book, every film, every website, every scientific paper, every whispered secret committed to a server, would be less than a single drop of water in an ocean the size of a galaxy compared to the H. Information that is at this very moment times you asterisk. This is the first great wall we face. It is a wall of pure information, a barrier built from the dizzying complexity of what it means to be a physical object in our universe. To even contemplate reading this data, let alone transmitting and reconstructing it, is to stand at the foot of an informational Everest with no tools and no path to the summit. The problem is not just one of big data. It is a confrontation with a scale of data that transcends any technological paradigm we have ever conceived. But let us, for the sake of our journey, imagine we could somehow invent a storage medium capable of holding this cosmic library of information. Let us pretend we have a cosmic hard drive with infinite capacity. Now we face a far more insidious and fundamental barrier, a trapdoor built into the very floor of reality by quantum mechanics itself. The problem is this: how do you read the data in the first place? How do you perform the scan? In our macroscopic world, observation seems passive. You can look at a statue, measure its dimensions, and note its composition without changing it. But in the quantum realm, the act of looking is an act of profound violence. To measure a quantum particle's property, its spin, for instance, you must interact with it. You have to poke it to bounce another particle off it, to probe it with an energy field. The instant you do, you inevitably and irrevocably change its state. The famous Heisenberg uncertainty principle is a direct consequence of this. You can know a particle's position with precision, but in doing so, you obliterate any precise knowledge of its momentum. Or you can measure its momentum, but its position becomes a smear of probability. You can never ever know everything about it at once. This is not a limitation of our instruments. It is not something we can fix with a better microscope. It is a core tenet of the universe. The quantum world is intrinsically shy. It does not allow for perfect passive observation. Now apply this immutable law to the 7 octillion particles that make up your body. To determine the quantum state of a single electron in a single neuron firing in your brain, you would need to probe it. The moment your hypothetical scanner touches it, that electron's state is altered or even destroyed. The original information you sought to capture is gone, replaced by the new state caused by your measurement. You would be trying to read a book written in ink that vanishes the moment light touches the page. To scan your brain to capture a thought, you would have to interact with every particle involved in that thought, thereby scrambling the very neural processes that constitute it. You would, in the most literal sense, be destroying the information as you read it. The scan required for teleportation would not be a gentle, non-invasive procedure. It would be an act of total, instantaneous and complete disassembly. It would be a process of vaporizing the original particle by particle just to get a blurry, incomplete and fundamentally flawed copy of the blueprint. This is the observer's curse, a terrible paradox where the price of knowledge is the destruction of the very thing you wish to know. You cannot know the living system without killing it. This leads us directly to the third and perhaps most elegant cosmic prohibition, the no-cloning theorem. This is one of the most profound and deceptively simple principles in all of physics. It states with mathematical certainty that it is impossible to create an independent and identical copy of an arbitrary unknown quantum state. You cannot simply scan a quantum system and then use that information to build a perfect duplicate elsewhere, leaving the original intact. The universe at its most fundamental level forbids perfect counterfeiting. Think of it as nature's ultimate copyright protection. The reasoning flows directly from the measurement problem we just explored, because you can never perfectly know the complete state of the original particle without disturbing it. You can never acquire the complete, perfect information needed to create a flawless copy. Any scan will be incomplete, and therefore any clone will be an approximation, an echo, not a true replica. Quantum teleportation, as we have seen it work for single photons, cleverly exploits a loophole in this law. It doesn't clone the particle. Instead, it transfers the quantum state from the original particle to another distant particle that has been previously entangled with it. But in this process, the quantum state of the original particle is destroyed. The information is not copied. It is times moved asterisk. The original ceases to be what it was. This is the fundamental trade-off. This is why teleportation requires the original to be annihilated. You cannot have it both ways. And this is where the true horror of the endeavor begins to set in. We are no longer talking about a benign form of travel. We are talking about a process that by definition requires the absolute obliteration of the original person. So let's combine these hurdles. First, you are scanned by a machine that must, by the laws of physics, get an imperfect reading of your quantum state. Second, this imperfect scan requires the complete destruction of your original body. Third, this flawed data is then transmitted to the destination where a new body is constructed. The being that walks out of the receiver will not be a perfect copy. It will be an approximation built from a corrupted data file. What would the consequences of such imperfections be? A single quantum bit flip, a misplaced spin on a single atom within a strand of DNA, could result in a catastrophic genetic mutation. A slight error in the momentum of particles within a prion protein could cause it to misfold, leading to fatal neurodegenerative disease. A subtle mistake in reconstructing the quantum states of the synapses in your brain could alter your memories, change your personality, or erase your very sense of self. Who or what would step out of that machine? It might look like you, it might talk like you, but with billions upon billions of potential quantum errors, it would be a ghost, a flawed echo haunted by the static of an imperfect transmission. The no-cloning theorem ensures that the teleported you would be a stranger, an imposter wearing your face. Even if we could wave a magic wand and make these fundamental physical laws disappear, the logistical and engineering challenges that remain are so colossal, they make building pyramids seem like playing with children's blocks. Let's start with the raw materials. The receiving station, your destination, would need to have a ready supply of all the necessary atoms to build you a vast cloud of carbon, hydrogen, oxygen, nitrogen, and all the other trace elements held in a state of perfect readiness. A sort of primordial human soup. Then there is the matter of entanglement, the very engine of teleportation. For the process to work, every single one of the 7 octillion particles in your body would need to be entangled with a corresponding particle in that raw material soup at the destination. We have struggled for decades to entangle a few thousand atoms under controlled laboratory conditions. The notion of entangling every particle in a complex, warm, wet living system like a human body with another set of particles trillions of miles away is so far beyond our capabilities that it borders on the absurd. The energy, the control, the precision required would be unimaginable. It would require a technology capable of manipulating the entire quantum state of a macroscopic object with single particle accuracy, a feat of engineering that would likely require the energy output of a star. And what of the data transmission? The quantum state information must be sent to the destination via a classical channel like a laser or radio signal, limited by the speed of light. As we've established, the amount of data is astronomical. Let's try to put that in perspective again. If you were to transmit the quantum data of a single human being using the entire combined bandwidth of every internet connection on Earth today, the transmission would not take hours or days or years. It would take longer than the current age of the universe. By the time your blueprint arrived at a destination even as close as Mars, the cosmos itself would be cold and dark. Your teleporter would require a communication channel so advanced it could transmit the entire history of the universe in a fraction of a second. This isn't an upgrade to our current internet. It is a fundamentally different conception of physics. Finally, there is the reassembly machine itself. This celestial 3D printer would have to take that data storm of information and with perfect fidelity assemble your body particle by particle. It would need robotic arms smaller than atoms, energy fields of impossible precision, all working in a perfectly shielded vacuum to place each of the 7 octillion particles in its exact quantum state relative to all the others. It would need to recreate every chemical bond, every folded protein, every neural connection, every subtle quantum vibration that makes you alive. The slightest error, a single misplaced atom, could be the difference between a living person and a heap of disorganized matter. The energy required to perform this atomic construction would be biblical, a celestial blowtorch capable of forging a human being from raw elements. We are talking about a construction project on the scale of a planet to build a single person. Each of these logistical hurdles, the entanglement, the bandwidth, the reassembly, is on its own considered by most physicists to be practically impossible. Taken together, they form a fortress of impossibility, a statement from the universe that some dreams are simply not meant to be realized. So we are left standing before this impenetrable wall, this series of seemingly absolute prohibitions. The sheer scale of the information, the destructive nature of measurement, the cosmic law against perfect copies, the nightmarish logistics of energy and engineering. It seems the universe has conspired to ensure that the flesh and blood, this intricate collection of particles, remains forever anchored to its place in space-time. The beautiful, elegant process we saw with a single photon shatters into a billion pieces when confronted with the glorious, messy complexity of a human life. It seems the final definitive answer is no, but this journey into the impossible raises a much deeper, more unsettling question, one that physics alone cannot answer. If you were to step into the scanner and your body was utterly destroyed, and a new body assembled from different atoms was created elsewhere, is that new person still you? Even if the copy were perfect, what has happened to the continuity of your consciousness? Where did times go in? That moment of annihilation, was a soul transferred, or was a life simply extinguished, and a convincing automaton created in its place? This is the paradox of identity, the ghost in the teleportation machine. We have smashed headfirst into the hard limits of physics, only to find ourselves adrift in the even murkier waters of philosophy. Perhaps then, our entire approach has been too literal, too crude. We have been so focused on deconstructing and reconstructing the physical body, this vessel of atoms, that we may have missed the point entirely. The universe has told us in no uncertain terms that moving the hardware this way is a fool's errand. But what if there is another path? What if the key is not to teleport the vessel at all? What if the true challenge, the real frontier, is not about moving the body, but about moving the mind? And so we arrive at the precipice of the ultimate question, the very question that has fueled this entire journey through the bewildering quantum realm. After witnessing the successful teleportation of single photons, of atoms of complex molecular information across laboratory benches and even between distant satellites, the human dream, the fantasy etched into our culture by decades, science fiction feels tantalizingly close. You have followed the breadcrumbs of entanglement, wrestled with the paradoxes of superposition, and seen the ghostly action at a distance made real. Now you must ask the question that beats at the heart of it all. Can we do it? Can we teleport a human being? The answer, delivered not with disappointment, but with the profound clarity of physical law, is an unequivocal and resounding no. Not now, not in 1,000 years, not ever in the way our fictions have imagined it. The dream of stepping onto a platform, dissolving into a shimmering column of light, and rematerializing on a distant world is and will remain precisely that, a dream. To understand why this beautiful fantasy shatters against the unyielding wall of reality, we must move beyond the scale of single particles and confront the staggering, almost incomprehensible complexity of a single human being. You are not a simple qubit existing in a delicate superposition of two states. You are a symphony of around 7 octillion atoms. That's a 7 with 27 zeros after it, each with its own quantum state, its own position, its own momentum, its own intricate entanglement with its neighbors. To teleport you, we would need to scan and know the exact quantum state of every single one of those atoms simultaneously. This is not a mere data collection problem. It is a fundamental impossibility. The Heisenberg uncertainty principle, the bedrock of quantum mechanics we explored earlier, stands as an eternal sentinel at this gate. It dictates a cosmic trade-off. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. A perfect, instantaneous scan of your entire atomic structure is forbidden by the universe's most basic operating manual. Any attempt to measure a particle with such flawless precision would be akin to trying to capture a soap bubble by hitting it with a hammer. The act of measurement would inject so much energy into the system that it would utterly destroy it, obliterating the very information we sought to capture. But even if we could somehow circumvent this, a still more profound barrier rises to meet us: the no-cloning theorem. This ironclad law, a direct consequence of quantum mechanics, states that it is impossible to create an identical independent copy of an arbitrary unknown quantum state. You cannot simply scan the blueprint of a qubit and fax it to another location to build a perfect replica. The process of teleportation we have witnessed is not duplication. It is a subtle and beautiful act of transference. To teleport that single atom, remember its original state had to be destroyed at the source, the very instant it was recreated at the destination. The quantum information, the very soul of the particle, was moved, but the original vessel was sacrificed. Now apply that terrifying logic to a human being. The process would not be transportation. It would be disintegration and reconstruction. The machine would scan you, destroying you atom by atom in the process to gather the blueprint. A new collection of atoms at the destination would then be arranged into a perfect facsimile. A person would walk out of the receiving chamber, looking like you, talking like you, holding all of your memories. But would it be you? or would it be a perfect copy born at the exact moment of your death? This is no longer a question of physics, but one of philosophy, of consciousness, of the very nature of identity. And it is a chilling question that thankfully the laws of physics themselves prevent us from ever having to answer. The beautiful, sleek teleporter of our imagination is in reality a suicide and reconstruction machine. Here then is where our story takes its most crucial turn. We must let the science fiction dream die, for in its place, a reality far more profound and powerful is waiting to be born. We have been asking the wrong question all along. The miracle of quantum teleportation was never about moving matter. It has always been about moving something infinitely more fundamental, more elusive, and more powerful, pure information. It is not a technology for transporting bodies. It is the ultimate protocol for transporting the very essence of reality itself. Think of it not as a cosmic moving van, but as a celestial telegraph capable of transmitting a message so perfect it carries the identity of the sender with it. When we teleport a qubit, we are not sending the particle itself. The atoms that make up the qubit at the destination are already there waiting. What we are sending is its quantum state, its precise orientation, its delicate superposition, its intricate web of entanglements. We are sending the ghostly blueprint, the informational DNA that makes that particle unique among all others in the universe. The destination particle times becomes times the original. It does not just receive a copy of the message, it is transformed into the message itself. This is the paradigm shift. We are not moving the orchestra from one concert hall to another. We are teleporting the symphony, the ineffable, intangible pattern of notes and rhythms, and allowing a new orchestra to play it with such perfect fidelity that it is indistinguishable from the original performance. And with this new understanding, we pivot from a closed door to an open universe of possibility. If quantum teleportation is the perfect way to move quantum information, then what can we build with it? The answer will redefine the 21st century. It is the key to unlocking the two most transformative technologies humanity has ever conceived, the quantum computer and the quantum internet. We stand today in an age of classical information, an era of ones and zeros of bits that are either on or off. This digital language has built our modern world from the smartphone in your pocket to the global financial markets. But it is a child's language compared to the poetry the universe is truly written in. The coming era is quantum, and teleportation is the very backbone upon which it will be constructed. Imagine a new kind of internet, a global network, not of electrons flowing through copper wires, but of entangled particles bound by ghostly connection. In this quantum internet, the nodes would be powerful quantum computers, processors capable of manipulating the strange logic of superposition and entanglement. How would these computers talk to each other across continents? How would they share the results of their staggeringly complex calculations without that precious quantum information being corrupted by the slightest noise or observation to the outside world? They would do it through teleportation. A quantum state calculated in a laboratory in Tokyo could be perfectly teleported to a processor in New York, its fragile superposition arriving intact, its entanglement preserved, its essence moved without ever physically traversing the space in between. This isn't about speed. The information transfer in quantum teleportation is still limited by the speed of light, because as we've seen, a classical signal is required to complete the process. The revolution is in the times, quality times, and time security times of the information being sent. It is the only known method for moving a delicate quantum state from one point to another with perfect fidelity. It is the ultimate shielded cable, a data transfer protocol whose integrity is guaranteed by the fundamental laws of physics. We are talking about building a planetary nervous system, a web of entanglement that allows quantum processors to be linked into a single global computational entity. This network would allow us to tackle problems that are currently impossibly far beyond our reach, designing revolutionary new medicines molecule by molecule, creating new materials with unimaginable properties, and modeling the Earth's climate with a precision we can only dream of today. This leads us to the most immediate and perhaps most disruptive application of this technology, the creation of a truly unhackable communications network. Every secret you have ever sent online, your bank details, your private messages, your government's most sensitive intelligence is protected by classical encryption. This encryption relies on mathematical problems that are incredibly difficult for today's computers to solve. But incredibly difficult is not the same as impossible. A sufficiently powerful computer, particularly a future quantum computer, could theoretically crack many of the codes that protect our global infrastructure, laying bare the secrets of the world. Our entire digital civilization is built on a foundation of locks that could one day be picked. Quantum communication enabled by teleportation and entanglement changes the game entirely. Its security is not based on a challenging mathematical puzzle. It is based on the immutable laws of physics. Imagine two individuals, let's call them Alice and Bob, sharing a stream of entangled particles to create a secret key for their messages. If an eavesdropper Eve tries to intercept and measure one of those particles to learn the key, the very act of her observation will instantly break the entanglement and alter the quantum state of its twin. Alice and Bob would see this disturbance immediately. The universe itself would act as an alarm bell. It is as if a secret letter, were it to be opened by anyone other than the intended recipient, would instantly burst into flames, leaving behind only the ash of a failed attempt at espionage. This is not encryption. It is a physical, unbreakable seal. Teleporting quantum states to build these secret keys would create a communication channel where privacy is not a promise made by software, but a guarantee made by reality. For finance, for national security, for personal privacy, the implications are staggering. It would herald the end of digital eavesdropping as we know it, creating a world where secure communication is finally truly secure. We are not just building a better lock, we are fundamentally changing the nature of locked doors, forging them from the very fabric of space-time. And at the heart of this web, at the nodes of this secure internet, lie the quantum computers themselves. These are not simply faster versions of the machine on your desk. They are a completely different kind of thinking machine. By harnessing the power of qubits to exist in multiple states at once, they can explore a vast landscape of possible solutions to a problem simultaneously. A classical computer walks through a maze, trying one path, then another, then another. A quantum computer, in a way, explores every possible path all at once. For certain types of problems in optimization, drug discovery, and artificial intelligence, their power will be almost godlike. But this immense power comes at a cost. Quantum states are unbelievably fragile. The slightest vibration, a stray magnetic field, a single stray photon, can cause the entire computation to collapse in a process called decoherence. A quantum computer is an oasis of perfect order in a universe of chaos. So how do you build a large-scale, fault-tolerant quantum computer? How do you move information from one part of the processor to another without it being corrupted? You teleport it. Within the crystalline lattice of the quantum chip itself, teleportation will act as the perfect noise-free wire, a quantum bus that ferries delicate qubits between logic gates, preserving their precious coherent state. It will be the invisible, silent scaffolding that allows us to build the cathedrals of computation of the next century. So the dream of human teleportation, the iconic shimmer of science fiction, dissolves. It was a beautiful but ultimately naive interpretation of a far stranger and more wonderful truth. We looked at this incredible phenomenon and saw a shortcut for our bodies, a way to cheat distance. But the universe was offering us something infinitely more valuable. It was offering us a way to move the fundamental building blocks of reality, the pure quantum information that writes the source code for everything that is, was, and ever will be. It was offering us the tools to build a new human epoch defined by computational power beyond imagination and communication, secured by the laws of creation. The quest to teleport ourselves has failed, but in that failure we have discovered the keys to a new kingdom. We have found the mechanism that will wire together the quantum age, the engine of a revolution that will change our relationship with information, with computation, and with secrecy forever. We have laid the theoretical groundwork for a global quantum network. The vision is clear, the physics is sound. And now the great and monumental challenge of our time, the focus of thousands of brilliant minds in laboratories around the world, is to move from theory to reality. How do we tame entanglement? How do we build the machines that can send and receive these ghostly messages, not just across a tabletop, but across oceans and continents. The blueprint is in our hands. The next great chapter is about the building. And so we arrive at the end of our journey, standing before the very question that launched our entire inquiry. After witnessing the ghostly dance of entangled photons, after tracing the delicate transfer of a single atom's soul across a laboratory, can we one day teleport a human being? The answer, forged in the crucible of quantum mechanics and tempered by the staggering complexity of biology, is almost certainly no. Not in the way our dreams have always imagined it. It is a conclusion that may feel like a disappointment, a closing door on a cherished science fiction fantasy. But to see it that way is to miss the profound, almost miraculous revelation that this quest has given us. We began by asking how to move a body from one point to another, and in the process we have been forced to redefine what a body, a point, and the very space between them truly are. The barrier isn't merely technological, a problem of engineering to be solved by the next generation's brighter minds. It is a barrier woven into the fundamental nature of existence. We have seen the breathtaking avalanche of data required to map a single simple molecule. Now, try to imagine the data that describes you, not just the static blueprint of your 37 trillion cells, but the dynamic, ever-changing electrical symphony of your 100 billion neurons. It is a torrent of information so vast it would dwarf every word ever spoken, every book ever written by our species. To capture that state in a single frozen instant, without violating the Heisenberg uncertainty that governs all things, is a computational problem of godlike proportions. And even if we could capture it, the energy needed to transmit that colossal dataset would require the power of a star. But beyond the physics, beyond the mind-bending mathematics, lies a deeper, more personal abyss. The ship of Theseus paradox, which we touched upon, ceases to be a philosopher's parlor game and becomes a terrifyingly practical question. If we were to scan your every particle, destroying the original in the process, would the person reassembled at the destination truly be you? Or would it be a perfect yet soulless copy, an echo with your memories, your hopes, your fears, but with the continuity of your consciousness, that unbroken thread of awareness you call a soul severed forever? The original you would experience only annihilation. Quantum mechanics offers no solace here. It provides a blueprint for rebuilding the house brick by perfect brick, but it cannot guarantee the ghost that haunted its halls will follow. It is here that the clean logic of physics collides with the messy, ineffable mystery of what it means to be alive. The dream of human teleportation in its pursuit has taught us the most humbling lesson of all, that we are not simply collections of particles to be scanned and reassembled. We are processes. We are symphonies of unfolding information, and the music we have discovered cannot be separated from the instrument. So the door to the transporter room swings shut. But look where we are standing now. Look at the landscape this seemingly impossible quest has revealed to us. We set out to find a shortcut through space, and instead we found a hidden door into the operating system of reality itself. The pursuit of teleportation forced humanity to take the bizarre, counterintuitive weirdness of the quantum world seriously. It compelled us to transform entanglement from a spooky philosophical footnote in a debate between Einstein and Bohr into a tangible, harnessable resource. It was the ultimate what-if question, and in trying to answer it, we accidentally stumbled upon the foundational principles of a new technological age. The treasure, it turns out, was never the destination, but the map we were forced to draw to try and get there. This map has a name. It is the map of the quantum age, and its continents are built from the very principles that make human teleportation so intractable. The ferocious precision required to scan a quantum state, a process so delicate it borders on the impossible for a living being, is the very same precision that is now allowing us to build the most sensitive instruments in human history. We are building quantum sensors that can feel the subtle gravitational pull of a single drop of water hidden deep underground. Medical devices that can map the magnetic fields of a living brain with such fidelity that they can witness a single thought taking form. We are using the fragility of quantum states not as a limitation but as a superpower, a way to listen to the universe's most subtle whispers, from the folding of a protein to the faint tremor of a distant black hole merger rippling through space-time itself. And what of the classical information channel, the beam of light or radio waves that must accompany the entangled particles to complete the teleportation? In our story, it was the Achilles heel, the speed of light limitation. That meant our quantum teleportation was never truly instantaneous. But in the real world, this partnership between quantum weirdness and classical data has given birth to the dream of a quantum internet. Imagine a global network not held together by vulnerable bits of ones and zeros, but by the unbreakable bond of entanglement. A communication system where your data is not merely encrypted but is encoded into the very fabric of reality. Any attempt to eavesdrop on an entangled message would require a measurement, and that very act of measurement would instantly shatter the delicate quantum state, leaving behind an unmistakable signature of tampering. It is a network that offers the promise of truly private communication, its security guaranteed not by a clever algorithm, but by the fundamental laws of physics. Your secrets, your financial data, your most private conversations would be protected by the same principle that once made Einstein so uneasy. Spooky action at a distance is poised to become the guardian of our digital lives. This quantum network will be the backbone for the most revolutionary technology of all, the direct intellectual descendant of the teleportation problem, the quantum computer. We have learned that nature is not classical. It does not calculate with simple ones and zeros. At its deepest level, reality is a seething foam of probabilities of superpositions of particles existing in a ghostly blend of all possible states at once. A classical computer, no matter how powerful, is like a tourist trying to speak a foreign language with a phrasebook. It can approximate it, can get the job done, but it will never be fluent. A quantum computer, on the other hand, speaks the native tongue of the universe. It uses superposition and entanglement to create a computational space of unimaginable vastness. A single quantum bit, a qubit, is not just a 1 or a 0, it is a 1 times and times a 0 simultaneously. With just a few hundred of these qubits, we can create a machine that can hold more possible states than there are atoms in the known universe. This is not just about building a faster computer to crack codes or model the stock market. It is about building a machine that can simulate reality itself. Imagine being able to design new medicines not through slow, painstaking trial and error, but by creating a perfect quantum simulation of a virus and a drug molecule, allowing them to interact inside the computer just as they would in a human cell. Imagine discovering new materials for superconductors or hyper-efficient batteries by building them atom by atom in a virtual quantum space, testing their properties before a single gram is ever synthesized in a lab. These machines could help us unravel the lingering mysteries of the cosmos, simulating the conditions inside a black hole's event horizon, or the very first moments after the Big Bang. They are our Rosetta Stone for the quantum realm, allowing us to finally read the source code of creation. This is the true legacy of our quest. We sought to copy a human, and in our failure we are learning how to copy a universe. Our journey began with a simple human desire to be somewhere else instantly. It was a desire for freedom from the tyranny of distance, the friction of space and time. What we discovered is that reality is far stranger and more interconnected than we ever dreamed. We are not isolated objects moving through a passive, empty void. We are participants in a vast quantum web. The atoms in your body are entangled with particles scattered across the galaxy, remnants of ancient stars that forged you in their fiery hearts. The information that constitutes you is not confined to the volume of your skin, but is encoded in a pattern of relationships and interactions that stretches out into the cosmos. You are a localized ripple in a universal quantum field. The future that quantum mechanics promises is not one of deconstruction and reconstruction, of beaming our bodies across the stars. It is something far more profound. It is a future where we learn to speak the fundamental language of information that underpins all of existence. A future where our technologies are no longer crude classical approximations, but are as subtle and as powerful as nature itself. We will not step onto a transporter pad, but we will wield the power of entanglement to connect our world in ways that are instantaneous and unbreakable. We will not dissolve into a stream of data, but we will use quantum simulators to understand the data stream of the universe itself. The dream of teleportation was a testament to our imagination, a story we told ourselves about mastering the physical world. But the reality of quantum science is the story of the physical world teaching us about the nature of imagination, information, and identity. We have learned that the universe is not a collection of things, but a network of connections. And that perhaps the most important journey is not the one across empty space, but the one that takes us deeper into the intricate, shimmering, and impossibly beautiful structure of reality. The quantum age is dawning, and though we may remain bound to our small world for a little while longer, our understanding is finally becoming as limitless as the cosmos itself. We are not just explorers of the universe. We are the universe waking up and finally beginning to understand the rules of its own magnificent dream.